Alright, welcome to the second to last module of our CCNA training, and this is really going to be the meat and potatoes of our routing protocol stuff. So today we're going to talk about OSPF, and then EIGRP, and finally wrap it up with a little bit of IPv6. So there's quite a few different topics here, and I'm going to try to cover it a little bit more slowly than I normally do, so hopefully you can get the gist of what's going on here. So first off, let's talk about OSPF. So first, to summarize OSPF, OSPF is a link state protocol. That is to say, every single device that's running OSPF on this network knows about every single interface and what network those interfaces are connected to. So OSPF is classless. It allows variable length subnet masking, so we can do VLSM topologies. It has a really good convergence time, approximately 10 seconds, and is probably the best protocol for interaction with non-Cisco devices. I say this because OSPF, of the two protocols that we talk about on the CCNA that are serious routing protocols, OSPF is the only open source one. It's fairly widely known, it's fairly widely implemented, and while it's a little bit more CPU intensive, it's fairly robust. OSPF, as I mentioned, is fairly CPU intensive, and so OSPF didn't really take hold until we started seeing a little bit beefier router. Now, the first thing I'm going to talk about with OSPF is adjacency. And basically, before routers can exchange their link state information, they have to become neighbors in an adjacent state. And so what will happen is they'll become adjacent. It's established when the following criteria match, and you should know these for the CCNA. We need to make sure that the hello interval matches. This is 10 seconds by default. The dead interval matches. This is typically 4 times the hello interval. The OSPF area ID, so the router should be in the same OSPF area. And then also the authentication credential should also match. There are also some OSPF options that should match too. I'm not going to go into those in high detail, but you need to know that they do need to match. Once the routers are neighbors, each router looks for a hello messages sent by the other router, and it's going to look for those every hello interval. So every 10 seconds is expecting a hello from the router across the way. Now we look at the OSPF router ID, and this router ID is typically 32 bits long and typically written in dot decimal notation. I wonder what else that we know about that's 32 bits long and typically written in dot decimal notation. And if you're thinking of an IP address, you're on the right track. So typically an OSPF router ID is written to look exactly like an IP address, and typically it is an IP address that the router is configured with. It may be administered directly. You can directly configure a router's OSPF router ID. You can also configure it with a loopback interface. So if a loopback interface is configured, then the highest loopback address, that is to say the highest IP address that is configured as a loopback, will become the router ID. If neither of these two criteria are met, it's going to look at its actual interface IP addresses, and it's going to use the highest configured interface IP as the router ID. Once a router is participating in OSPF, its ID does not change. So if you add an interface with a higher IP address, say your ID right now is 192.168.1.1, and you add an interface 193.168.1.1, that would be a higher IP address, but the OSPF router ID will not change once it's participating in an OSPF. So now we're going to look at the different link types for OSPF. The first type that you'll need to know about is point-to-point, and this is used for point-to-point networks. Basically, you have 2 endpoints, and those are the only possible hosts that you'll have. Adjacency is established with both routers on the link. So there are only 2 routers, so we should establish an adjacency between both of them. That makes sense, right? So now we're going to talk about broadcast domains. These are a little bit more complicated. So when a network supports broadcast traffic, ideally, I don't think you'd want to establish an adjacency between every single router on the same broadcast network. You shouldn't do this for a lot of reasons, and the primary one is because the number of adjacencies increases exponentially as the number of routers increases. So, say I have 10 routers, that's going to be a lot of adjacencies on the network. Basically, every single router is going to have 9 adjacency, so you're going to have 90 different adjacencies. And then, you also have it's a nightmare. So basically what happens on a broadcast network like Ethernet, for example, is that you have a designated router and you have a backup designated router. And so what happens is all of these different routers elect a DR and they elect a BDR. And basically what happens is, rather than establishing adjacencies with every other router around them, they only establish adjacencies with the DR and BDR. And this prevents, as many adjacencies from being formed. It actually helps a lot. And so the DR and BDR are only elected when you have a broadcast network. Now, here's the election process, and I just kind of jotted it down here real quick. So if a DR and BDR have already been selected, the values are accepted. In other words, once a DR and BDR are elected, they're not going to change until one of them goes down. If a designated router fails, then the backup designated router takes its place. That makes sense, right? And a new BDR is elected. If a router, basically, so let's say that no DR and BDR have been selected. The router with the highest priority will become the DR, and normally priority isn't set by you. It can be, and that's how you can force a DR or BDR. But if there's a tie in the priority, the router with the highest router ID will become the DR. And so this is where router IDs actually come into play, and you can configure these router IDs, or you can adjust the priority. The steps above are repeated to determine a BDR, and so you elect a DR and a BDR in this fashion. Again, highest priority or highest router ID. So now we're going to talk a little bit about the link state database. All routers have to send their neighbors a copy, their adjacent neighbors, a copy of this link state database. And this basically contains all of the interfaces in the network that the current router knows about. And it will go through and look for duplicate interfaces when it receives a link state database from another router, and it will, try to exchange this information, and basically by the time you converge, all the routers will have the same link state database. All the routers will also run the SPF algorithm and then to determine the shortest path to each network. This is actually an algorithm. I'm not going to go into the details, but basically it will look at the entire topology for your entire network to determine what the shortest path is. And then if there's a change in the topology, it'll have to rerun the SPF algorithm to determine what the new path will be. Large networks have huge link state databases, and so the goal here then is to minimize the size of the link state database. So for now we're going to talk a little bit about OSPF cost calculations. Basically, these vary by vendor, but typically with Cisco products, it's going to be 10 to the 8th divided by the bandwidth in kilobits per second. That's going to be considered your cost. Again, this is the inverse of bandwidth. So the way this works is that your higher bandwidth interfaces are going to result in a lower cost. And if you don't understand why this is, just do the math. Plug in a really high bandwidth number there and plug in a really low bandwidth number there, and you'll get, a higher bandwidth is going to have a lower cost. And so we're going to select the link with the lowest cost as our primary thing. So 10 to the 8th is 100 MIPS, and it's going to be the reference bandwidth. This actually causes issues when you have, say, a gigabit link. You're going to be dividing by 10 to the 8th by 10 to the 9th. So that will result in a number less than 1. The router will round up to 1, and so it turns out, by default, in OSPF, 100 MIPS links have the same OSPF cost as gigabit links. This is a problem, and you can actually adjust that top number, that 10 to the 8th, that reference bandwidth, with a command. We'll talk about that here in a bit. Bandwidth can be changed directly on an interface with a bandwidth command. You can configure it yourself, otherwise it'll take some defaults. You can configure it with IP OSPF cost and then the actual cost value. Whereas the first bandwidth will actually be plugged into the equation to determine the OSPF cost. The second command, you can actually just directly write the OSPF cost you want to use on the interface. And finally, we have that command that I was talking about that can adjust the reference bandwidth. Keep in mind that the reference bandwidth is in MIPS. I don't know why this is, because the calculation is done in kilobits per second. So auto cost reference bandwidth will actually adjust that reference bandwidth, that is that top number in the numerator there, to determine your OSPF cost. This is, like I said, very useful if you want your gigabit links to take precedence over your fast Ethernet links. OSPF will actually load balance between costs for equal cost paths, and again, the cost has to be equal, and it will install all of the routes that have the same cost. I believe by default that's 2, and you can actually adjust that to more with the command maximum paths and then the number of maximum paths that you want to have. So now we're going to talk a little bit about OSPF areas. The idea here is that we want to segment a single autonomous system into several different smaller areas. The goal is to keep our link state databases fairly small, because remember, SPF is a fairly CPU-intensive algorithm. We don't want to have to run it on a very large link state database, so it pays to actually subdivide your OSPF topology into different areas. In a multi-area network, you have to connect all areas to Area 0. Area 0 is considered the backbone area. And there are different routers that take different roles when you have a multi-area network. You have what's called an area border router, and this router was basically just an OSPF router that's been configured for 2 areas. You also have what's called an autonomous system border router. This is something you would have at the very edge of your network that would connect to another autonomous system using border gateway protocol. Okay, so we have our OSPF configuration now. This is basically how the OSPF is going to be configured. We have router OSPF and then a process ID. This is just a number that the OSPF process is running on. To add an OSPF, you have to add the network, and you'll notice there's a wildcard mask there, not a subnet mask, but a wildcard mask, and then you have to specify what area the network falls under. You can manually administer optionally the router ID with the router-id command. You can change the auto cost reference bandwidth as we mentioned before, and you can adjust the number of maximum paths for equal cost load balancing. Now, if you wanted to configure OSPF configurations on an interface, you can manually set the hello, dead interval, cost, and bandwidth on an interface directly. Authentication is a little bit more complicated with OSPF. You can do clear text authentication with a key, like it's shown here. You can do MD5 authentication with a key that's been hashed, or you can do no authentication, which is the default. Also, you can configure authentication for an entire area. This makes things a little bit easier. If you have several interfaces in the same area, you don't have to worry about trying to configure every single interface in that area. You can just configure area 0 authentication and then whatever sort of authentication you want to use. So here's some OSPF diagnostic commands: show IP route, show IP protocols to determine if OSPF is running, show IP OSPF. There are lots of different subcommands of show IP OSPF that are very handy. And then finally, debug IP OSPF will give you an idea of what's going on in the OSPF topology at current time. Now, I had to cover OSPF fairly quickly there. There's a lot more to it than just what I've discussed here. Again, I would encourage you to go through the textbooks, read up on OSPF, do some labs, try to get your hands dirty with this stuff, because it's very, very important that you have a practical working knowledge of OSPF. And again, if you have any questions or comments, please put them in the comment section below, and have a good day.